How's it going, everybody? In this video, I'm going to be talking about mostly capacitors and inductors. I'm also going to be talking about, let's see, transient response, magnitude response, RMS voltage, frequency, all that sort of good stuff. So hopefully this video will help you a little bit with understanding what's going on with these components, as well as what we will be doing in the next week's lab. So looking at the lab manual here, you can see we're learning about two new components today, capacitors and inductors. So both of these components are passive elements in the sense that they don't provide energy to the circuit, although interestingly they do store energy, but the only way they store energy is by receiving it from something like a power supply first, and then they can hold on to it and they can give it back later. So a couple important things about these components is that unlike resistors, they can, and most of them do, have polarity. So let's see, I have that somewhere here. Okay, so inductors, this is a circuit schematic for an inductor. It's basically a wire wound around a coil. That's all it really is in real life as well. So a rather, an inductor like this is not polarized, and an inductor that looks like this is polarized from a circuit schematic standpoint. And notice the only difference here is this little dot, and it has to do with coupling, which you aren't expected to know about, but generally, to be safe, look at the components, and if they have like a red terminal, that means it's the positive terminal, and you should always treat it as a positive terminal, and the black would be the negative terminal. So that's just a good rule of thumb. If they have those terminals on them, use them. If they don't, then they may be non-polarized like this, in which case you can hook them up either way and you won't damage anything. Capacitors also can be polarized and not polarized. The larger the capacitor, and same with the inductor, the more likely it is to be polarized. So capacitor like this with the plates that are just parallel typically means it's non-polarized, although not everyone follows this convention, so do be careful about that. Similarly, a polarized capacitor has this, and a lot of times they put a positive sign on the highest potential point in the circuit, and then they have this little curved plate at the bottom. That's supposed to indicate that the capacitor is polarized. So be aware of that. I'll talk about that in lab. It is possible to blow the top off your capacitor. It's happened in IME 156 before. If you hook your capacitor up backwards and you apply power, the top can literally pop off. So just something to be careful. And let's see what else I got in my handy dandy. Okay. So yeah, so you should look over the units for capacitors and inductors. Hopefully it will make a little more sense as to why they have the units they do. Also, if you want YouTube videos about how capacitors and inductors work, I would do that. It'll be pretty helpful. So let's look at these equations over here. These are the important defining equations for capacitors and inductors. So capacitors, the current through a capacitor is equal to the capacitance and times the derivative of the voltage with respect to time. And for an inductor, you just basically flip everything, currents and voltages rather. So the voltage across an inductor is equal to the inductance times the change in current over time. Similarly, they're going to be talking about RMS. Here's the equation for RMS. Decimal to dB, that's this conversion. You'll need to know this. And frequency to time. The period of a waveform is basically proportional to 1 over the frequency. So those will be coming back to here and there. So let's go to LT Spice and talk a little bit about different circuits. And first thing I want to talk about is the transient response. So if we go to the lab report, and we scroll down here, and there's the math. Talks about inductors. Make sure you read that. Before we talk about transients, let's talk about connections. So inductors add in series like resistors do. So this is a circuit schematic of 3 inductors in parallel, and the equivalent inductance is just the sum of the 3. The same as if you replace these with resistors, it's the same idea. And then with inductors, you can have parallel combinations like this, where they add in this sort of a fashion. And so we can see that right here. And you're not expected to know this, but if you're interested, it's because capacitors are, let's see if I can find it. Inductors, inductance is proportional to the number of turns. So basically, if you have a bunch of inductors stacked together, you're increasing the number of turns. And so as you increase the number of turns, the inductance increases. So if you look at this equation, it kind of makes sense. But we don't need to worry about that. So let's go back to here. Or rather, here we go. So so back to the lab manual. Capacitors are the opposite. So very important. Inductors add in series like resistors. Capacitors are flipped. So capacitors and inductors pretty much they flip everything. So if you know a definition or an equation for a capacitor, you can easily find it out for an inductor, usually just by flipping the different relationships. So capacitors add in parallel. So you can see here's a parallel network of capacitors, and the capacitance literally just adds. So it is, I guess, backwards from resistors. So just be aware of that. And similarly, capacitors in series act like this. So this would be the equation you would use if these capacitors were in series. So be aware of that. I'm not sure if we'll be using it in the lab, but you just need to know that. So next thing, let's talk about, I guess, period and frequency real quick. If you haven't learned in math class at some point, period and frequency are directly related to one another. So here's the equation I have. I have sine of 2 pi f, f is a frequency, times t, and t is just a random variable. I can also replace this 2 pi f with omega, so sometimes you'll see that. And the period is just equal to 1 over the frequency. So if somebody gives you a sine wave like this, you should be able to identify the frequency or the period. And also sometimes you multiply that 2 pi into the frequency. So be aware that somebody asks you for the frequency and it's given as a number like sine of 1000t. F is not equal to 1000 hertz. Okay? F is actually equal to 1000 hertz divided by 2 times pi, right? Because it's 2 pi here. You need to factor that out before you can find the frequency. So just be aware of that. And now let's talk about the transient response of a circuit. So in the lab manual there is, let's see, this picture right here, and this is a transient response of a capacitor charging. So here I have a real simple circuit. I have a resistor, a capacitor, and a voltage source. My resistor is chosen, it doesn't really matter a whole lot, so 1 kilo ohm. My capacitor here, 1 microfarad, that's a pretty reasonable value for capacitors. A lot of times you see capacitors in the nanofarad or microfarad range. So what I'm going to be doing here is I'm going to be applying a pulse function. So you don't know how to do that yet. So if we right click on this voltage source and then we look at the options. So normally it would come up with, here, let's see if I delete this. Let me put it back in. Put in this voltage source. So if you right click it, you usually get this basic GUI here. And it's asking you for a DC value. Well, we don't want a DC value, we want a more advanced system. So we're going to go advanced. And we want a pulse. And a pulse is just a square wave. So we're going to click pulse. And V initial, this is asking where the voltage is going to start at. So for us, we're going to start at 0 volts. V on is asking what the voltage is when the pulse goes high. So we want to go to 5 volts. So this is saying from 0 to 5 volts. The delay, this is asking when you want to start your pulse. And I'm going to start it at half a millisecond so I can just see that it's 0 volts initially. T rise and T fall, I'm going to put 1p. What is 1p? P stands for picosecond, so that's 10 to the minus 12 seconds. And you do need to define these values, and all this is saying is that your square wave is going to go up and down really fast. It's not going to take a long time for it to rise or a long time for it to fall. And this is good because you want an ideal square wave, which actually has an infinitely fast rise time and an infinitely fast fall time. You also should define T on. I'll just put 10 milliseconds. And that'll basically say the pulse is going to stay high at 5 volts for 10 milliseconds. So click OK. And I don't like how it's over here, so I'm going to move it over here. And then I did a transient response. So if I go to my simulate and I click Edit Simulation Command, you bring up this edit command card here. And what I'm going to do is I'm going to simulate it for 5 milliseconds, so that's the stop time. I'm going to start saving data at 0 or 0 milliseconds, I guess. And maximum time step, just asking how many data points you want to take. So I'm going to do every tenth of a millisecond. That's usually good. So click OK, and it'll pop this up. And now if I click Simulate Run, well, I got a bunch of things going, but this is the plot I want to look at. So I'm going to look at the voltage across this capacitor. So if you just click there, and all I did was click, it'll bring it up here. And you can see, boom, I have a transient response, and by transient it means time domain. So on the bottom here you can see the time. And then the voltage is over here on the left. So if I go back to the lab report, it looks very similar to what this guy has here. The other thing you can bring up is you probably want this square waveform just so you can see what's happening. So let's go back to our circuit schematic. And I'm going to grab the voltage at this node here since that's the incoming square wave. So I click that, and now if I come over here. So now you can kind of see it. I have this blue waveform up top, which is my square wave. It rises almost instantly, so it's basically a perfect square wave. And since your capacitor can't change instantly, it actually takes some time for the voltage to charge. So the capacitor has an exponential equation that says how long it takes for it to charge. And basically, in theory, this voltage up here will continue to approach this 5-volt limit, but it will never actually hit that. It'll just get closer and closer. So as you can see right here, it's already starting to level out. And it would do this if I did a transient response for a lot longer. It would basically just flatten out. And if you're interested, you can calculate the time it'll take to charge, and that's the time it takes for the capacitor to get to 0.707 of the maximum voltage, so that's 3.53. And you can calculate that charge time by just multiplying the resistance in the circuit times the capacitance, and that's right here. So about 1 millisecond is the time I would expect it to get to this 3.53 volts. So let's go ahead and look over here and just make sure that's right. So I'm actually starting at 0.5 milliseconds because that's when I see this pulse. So 1 millisecond from there is going to be 1.5. And, okay, so about 3.53, I think it's about there. So you can see we're getting pretty close to about that 1 millisecond interval. I'm not sure why it's not exactly 1 millisecond. I'll have to look at that. But that's pretty much it. So that's the idea of a transient response. And actually, while we're doing this, let's go ahead and do the same thing for a inductor circuit so we can see how that works. So the transient response of an inductor circuit, here's a circuit. I did a pulse function, so I'm going to be sending in a square wave, and I did a transient response. It's already set up, and you can look at my component values here. And I'll go ahead and click Run, and bring up this data. And I'll put the square wave by clicking right here, and I'll put the capacitor voltage by clicking here. If I go back here, you can see my square wave is in green, and it looks like my inductor response is in blue. So an inductor is the reverse of a capacitor. So instead of coming up slowly and charging and staying at this 5 volts, the inductor actually does the other thing. It starts here at 5 volts and then it drops down to 0. So it's a very important fundamental difference. Capacitors for DC voltage, and basically all this step response is a DC voltage, right? Because this voltage at 5 volts isn't changing. So for an inductor, a DC voltage applied to it will make a short circuit. And for a capacitor, a DC voltage will make an open circuit. So that's very important. Let's go ahead and write that down. That's a really important defining component. So capacitor, I don't really have time spelling today. Capacitor is DC open. Inductor is DC short. So that's really important. So let's remember that. So I think I'm going to cut it off for this video. In the next video I will talk about inductors, and I will also be talking about magnitude responses and RMS voltage. So go ahead and watch that, and hope you enjoyed this one.